Hello and welcome back to Geometry. We are in Chapter 4, Section 3, Rotations. Alright, a rotation is a rigid motion about a point. Now that point is called the center of rotation. If that point is part of, the point can either be part of the figure or it can be outside of the figure. Now if it's outside of the figure, then the distance from one of the points to the point of rotation, to the center of rotation. What's happening? This distance, so from Q to P, that distance is going to be the same distance. Oh, it's going to be the same distance. I have a little trouble here. Anyways, as this line right here from Q to P. Okay, now rotations can be clockwise or counterclockwise, but for most purposes, unless otherwise specified, it's going to be counterclockwise. And we have an angle of rotation here, usually specified from where the figure was initially to where it is now. All right. We can have different degrees of rotations, and there are special ones that'll do certain things to the coordinates. So we're going to look at that now. Let's see, we will have a point like this. Let's go from there. That'll work. Okay, so this will be my initial point right here, A. Okay, and we're going to do a rotation of this. Now A is at 4, 3, right? 4, 3, and we're going to rotate that by 90 degrees. So this right here is 90 degrees to this point, A prime. That point is now -3 and 4. -3 and 4. So that was a 90-degree rotation. Now another 90-degree rotation means from my initial point to the next point, at this point right here, this is a 180-degree rotation. 180 degrees. This point right here, let's just do 2 primes. That is -4 and -3. And then the last rotation all the way around to here, that's 270 degrees. This point, sure, I'll just do a triple prime, there we go, is 3 and -4. Now if you'll compare these coordinates, so from my first point to get 90 degrees, okay, let's see, rotation. If I have a 90-degree rotation, I go from having AB to having, notice we flipped them around and the B was negative B, A. From the initial point AB, if I do a 180-degree rotation, then all that changes is my signs flip. I have -A and -B. If I do a 270-degree rotation, then my numbers flip and A gets negated. So I have B and A, and this one gets negated. Alright, so those are special cases, useful to remember. Another way that you can do one of these rotations, we'll look at an example here. So we have here vertices R, S, T, and U. And they say to rotate this 270 degrees about the origin. That means the origin is going to be our center of rotation. Now you could just measure 90 degrees every time. You could say, well, R right here is down 1 over 3. So now I'm going to rotate these 3 by 90 degrees. And then I'd have to have 1 going that way. So I'd go up 3 over 1. And there I could find my new point. I had to rotate this to here. And there's the new R. That's R prime. And then I could keep going by 90-degree increments if you don't remember our super trick from a moment ago. Alright, but the super trick you just learned was that by a rotation of 270 degrees, we go from our initial AB to, remember, we flip BA, and A gets negated. So we're going to flip these two, 1 and 3, and negate this first one. So 1 and 3. That means this is going to be R prime right here. And then same thing here, flip 1 and -5, negate this one. So 1 and -5. S prime. T prime is going to be 3, -3, and -5. -3, -5 is T prime. And then U prime is -1, -2. -1, -2. And there is our rotation of 270 degrees. U prime. So we went from R all the way around the origin to here, 270 degrees. Same thing, U. Went all the way around the origin to here. And same thing with the other points. Alright, now postulate 4.3 tells us that a rotation is a rigid motion. That means none of the angles change, so my angle D is going to be the same as the measure of angle D prime. And none of the side lengths change, so D to E is going to be congruent or the same measure as D prime to E prime. Alright, a composition means that we're going to do several moves. Alright, we have RS at 1 and -3, 1 and -3. Right here, that's R, and then S is at 2 and -6. So here is our initial shape. And we are to first reflect it in the x-axis, then rotate it 90 degrees about the origin. So reflect it, we're going to go across the y-axis. So 1 away, so 1 on this side. 2 away, so I'll go 2 on the other side. And there's our reflection. Here we have R prime and S prime. This was S. And now we want to rotate it 90 degrees about the origin. So about the origin, a couple ways we can do that. We can say, okay, we go 1 over, 3 up. So I can go 3 over, 1 down, this way, right? Up 3, sorry, right there. That's one way we can do that. Or you can remember your rules that a 90-degree rotation, if you have A and B, then a 90-degree rotation gives you -B and A. So 2 ways you can do it. You can either find your new points and flip them and negate B, or you can rotate it. I'll just choose to rotate it this time. I'm going 2 this way, and then 6 up. So I'm going to go 6 over, and 2 down, and there's my new point. So there's, well, change colors here. Here we go. R2 prime and S2 prime. And there's our new shape. So reflection across the y-axis, and then 90-degree rotation about the origin. All right, rotational symmetry is when you can take a shape and rotate it about a center of rotation, also called the center of symmetry, and you get the same shape. Okay, so it's reflected upon itself. Now, if I turn this one just 45 degrees, it's not the same shape. But if I turn it 90 degrees, this one turns onto itself, and this shape looks the same as the first shape. So it has 90-degree rotational symmetry at 90 degrees and 180. All right, let's see. Do they have rotational symmetry? If so, describe any rotations that map the figure onto itself. All right, a parallelogram. Does it have rotational symmetry? Yes, it does. 180 degrees. Okay, so this has rotational symmetry at 180 degrees. If I flip it 180, it maps itself onto itself. What about the octagon? It has multiple ones. Rotational symmetry, I can rotate it, that would be 40 degrees, and, no, sorry, 45, right here, 45 degrees, 90 degrees, 180, and, oh, we skipped one in between, because if I do another 45 from the 90, I can get to 135. 135, and then we do another 180. So 45, 90, 135, and 180. Oops. 135 is right there, and then 180 to here. Okay, the trapezoid. Does that have rotational symmetry? No, I can't rotate this onto itself. I have to go all the way around until it looks the same way again. Here we'll look at an example. There we go. Recreate this and rotate that around. See, if I turn it around, it's not going to look the same. It's going to be upside down. I rotate it this way. Nope. Nope. I've got to go all the way around. All right. Well, that is it for today. Check back in for another fun lesson next time.